Okay, so we're going to talk about acceleration, and acceleration is the change in velocity over a period of time. So I think it was assignment 8, but we did an assignment earlier where we actually calculated the speed at 20 seconds, and then we calculated the speed at 30 seconds. And then the next question asked us, was there any change in the speed? And there was, of course, change in the speed because we had some form of acceleration. So in order to calculate acceleration, it is delta V over t. And remember that delta is this Greek letter that means change. So delta V over t means the change in velocity over a period of time. And we calculate that by using final velocity, which is Vf, minus initial velocity, which is Vi, over the time. And that will give us the acceleration. Now, remember, the acceleration could be positive or it could be negative. It's just a change. We could be getting faster or we could be getting slower. Now, a little bit different with the graphs is the acceleration graphs are velocity in time. Okay, velocity in time. So we don't have distance over here. We actually have the velocity. And so on assignment, I think 12, when you were doing the speed graphs with instantaneous speed, I think you also did a acceleration graph, although you may not have known it. So we have a couple different shapes, and we need to talk about what happens with each of these shapes. Again, it's very important when you're looking at these graphs that you notice whether or not your y-axis is distance, because that would be a speed graph or velocity graph, or if your y-coordinate or your y-axis is velocity, because in that case, it's going to be acceleration. Okay? So if we have a positive slope, we have positive acceleration, meaning we are speeding up. If we have a negative slope, we have negative acceleration, which is often called deceleration. At this point, we are slowing down. And then if we have a flat line, we have no acceleration. Now, unlike the time-distance graph, we have a flat line. We are actually standing still. But in the acceleration graph, we are not standing still. We are still moving. We are just not changing our speed. So this would be the same thing as maybe cruise control. We're just staying at a constant velocity. All right, so what are the units for slope for the velocity time graph? And remember that the units for slope or meters per second or distance over time for the velocity graph, and for this one, the average acceleration is going to also be the slope. So if velocity is measured in meters per second and time is measured in second, then velocity time slope would be meters per second, okay? Because we would have meters per second here for the velocity and then per second. So that actually becomes meters per second squared. Okay, so delta V over t is acceleration. All right, so what happens when you have a curved graph? Because normally you're going to have a curved graph. If it curves up, it means that we're accelerating. If it curves down, it means that we're decelerating. So we can be accelerating and decelerating and not necessarily at a constant speed. Okay, depending on the steepness or the sharpness of the curve will tell us how fast or how slow we're going, how much we're speeding up or how much we're slowing down. So for instance, if you look at this one, you can tell that this blue line right here has a very sharp acceleration. It quickly speeds up. The green line, green cart or green traveler, has a more constant acceleration, okay? Whereas this orange one accelerates, but then starts to slow down here, okay? So we can tell a lot just by the shape of the graph. So the question here says, which line accelerated the fastest in the first 2 seconds? Well, in the first 2 seconds, the one that accelerates the fastest is actually the blue line, okay? But if I were to say which one accelerated the fastest in the first second, well, that is clearly the orange line, right? And then if I ask you which one has the most constant rate of acceleration, that would be the green, because it has the least curvature and is closest to the straight line. All right, so let's do the sample problem. So a car starts from a stoplight and travels with a velocity of 10 meters per second east in 20 seconds. What's the acceleration? All right, so we have to identify the initial velocity, the final velocity, and the time. Okay, so these are our variables. The final velocity is 10 meters per second. The initial velocity is 0, and we get that because it says it starts from a stoplight. So we know that the car is still. And the total time is 20. So the unknown is acceleration. That's what we're looking for. And the equation we're going to use is acceleration equals delta V over t. So we're going to substitute final velocity for 10 meters per second. Initial velocity is 0 meters per second. And we're going to divide that by 20 seconds. Okay. So when we do that, we get 10 meters per second because 10 minus 0 is 0. 10 minus 0 is 10, sorry. And 10 over 20 is 1/2. So we get 0.5 meters per second squared. So that's the acceleration for this car from the stoplight. So fill in your notes. I think there's a video for you guys to watch today as well. And then we'll do some text reading about acceleration also.